Okay, let's go ahead and get started with this. This set of notes should not take too long. There's only one concept here, and it's not that difficult of a concept. It's a little bit more difficult than a normal beginning of the unit concept usually is. So you're going to have to make sure that you pay attention to this one. But it's basically just building off of, or it's building on what we've talked about so far. Okay, so we've talked about how weak acids affect pH when added to water, how the weak bases would affect the pH. Obviously, weak acids are going to raise the pH, or lower the pH. Sorry, weak bases are going to raise it. And we've also talked about how salt solutions affect the pH. Okay. Now we're going to add both at the same time. Okay, and we're going to talk about what effect that has and how to calculate it. And it's not that difficult. It kind of combines the two concepts. And you can think about this one of two ways. You can think about it conceptually, or you can think about it using an ice table. The conceptual way of thinking about it would be more for if they just ask you a conceptual question, which direction is this going to shift the equilibrium? It's kind of a Le Chatelier type thing. If they actually ask you for a number, then obviously you're going to have to calculate it using an ice table. So I'll show you how this happens. Okay, so let's say that we have a solution that has acetic acid in it, the HC2H3O2. Okay, so it has the acetic acid in it, and we're going to add some sodium acetate into that solution, and we want to know what's going to happen at the pH of the solution. Okay, so the equilibrium equation here that we would want to think about when we have acetic acid in water. You can put the water in here. I'm taking the shortcut method with this. So H plus plus C2H3O2 minus. Okay. So there's our equilibrium equation, and now we can think in terms of Le Chatelier, because we've got the system in equilibrium, and what we're basically doing here by adding the salt is we're disturbing the equilibrium. Okay, now when we put this salt into water, it's going to, like any salt does, it's going to dissociate, okay, so into Na plus C2H3O2 minus. Okay, now the Na plus doesn't do anything in solution. We talked about that in the last chapter. But the C2H3O2 minus, well, that is this, right? So essentially what we're doing here, if you want to think about this in terms of Le Chatelier, when we put this salt into water, we're adding more of one of the products, okay? So again, thinking Le Chatelier, if we add a product, that pushes the equilibrium back towards the reactants, okay? Because now there's more of the C2H3O2 minus to react with the H plus, okay? So essentially what that's going to do is it's going to take some of the H plus out of that solution and turn it back into the acetic acid, the HC2H3O2, okay? When that happens, so we're adding more of the acetate, it's reacting with the H plus, the concentration of the H plus, okay, is going to go down. So what will happen to the equilibrium if we increase the concentration of the products? We already said that it's going to shift the equilibrium to the left. And then what will this do to the concentration of H plus in the solution? It's going to lower the H plus concentration, okay, because it shifts the equilibrium back towards the reactants. And so then if it does that, then it's actually going to raise the pH of the solution because now we have less H plus. So less H plus means we have a higher pH, okay? Now there's another way you can kind of think about that. I mean, the NaC2H3O2, because the sodium doesn't react, and the anion here, the acetate, acts like a base, typically in solution. Obviously, if you add a base to the solution, you would expect the pH to go up. Okay, so that's another way to also think about it. But it works to think about it in terms of Le Chatelier. If we add a product, it pushes the equilibrium back towards the reactants. If we add a reactant, it pushes the equilibrium towards the products. Okay, so ultimately that's what's going to happen here is we're going to lose some of our H plus, and that's going to raise the pH. Okay, that's called the common ion effect. All right. And what happens is a weak electrolyte, such as HC2H3O2, acetic acid, that is a weak electrolyte, it's a weak acid, it will actually ionize less if you add a strong electrolyte to it that has an ion in common with the weak electrolyte. Okay, so what we did is we added acetate ion to this solution. And what that ends up doing is it means that this is actually going to ionize less. Okay, in other words, there's going to be more of the HC2H3O2, the undissociated acetic acid, than there is of the H plus, and now there will be more C2H3O2 minus because we added that ion into the solution. Okay, but it actually pushes the equilibrium back towards the left side, so that means that less of the acetic acid will ionize, and that's called the common ion effect. Okay. What is the pH of a solution made by adding 0.30 moles of acetic acid and 0.30 moles of sodium acetate to enough water to make a liter of solution? All right. It may seem daunting at first, but this is really no different than the stuff that we've been doing before. The only thing that you have to keep in mind here is there's going to be some of the acetate at the beginning of this thing because we're adding the sodium acetate in as well. Okay, so when you do a problem like this, what you want to identify is what is the relevant equilibrium that's happening here. Okay, you put sodium acetate into water, it just dissociates. Okay, but the relevant equilibrium, the one that includes both this and the anion here, is the equilibrium for the dissociation of the acid. Okay, so we've got acetic acid. It dissociates to form H plus and C2H3O2 minus. Okay, the relevant equilibrium is going to include the acid and its conjugate base, or the base and its conjugate acid, just depends on which way you're doing it. Okay, so then I'm just going to make an ice table because I think that's always a good idea. We're adding 0.30 moles of acetic acid into 1 liter of solution. So that's, the 0.30 moles is the same thing as the concentration here. So we've got a 0.30 molar concentration of the acetic acid. Okay. Here's the weird part though. We're going to assume that we have none of the H plus. Now again, there's a little bit of H plus just coming from the water, from the auto-ionization of water, but that's so small we can assume it's nothing initially. Okay, but at the same time we're also adding 0.30 moles of sodium acetate to this thing. Okay, so we already have some acetate in that solution as well. Alright, so that's not zero. So then we just do our normal thing here. Now I guess the other thing that it would be good to know would be the Ka for the acetic acid. And I should have that memorized, we use it enough, but I don't, so let me look that up real fast. The Ka for acetic acid is 1.8 times 10 to the negative fifth. Okay, so now we have our Ka, and we have our initial concentrations, which is all that we need in order to solve one of these ice tables. Because we have none of the H plus, this equilibrium is going to have to shift to the right. Okay, it can't go to the left at first because there's no H plus for the acetate really to react with. So the acetic acid concentration is going to go down, and the concentration of the products is going to increase. So we end up with 0.30 minus x, x, and 0.30 plus x. Okay? And then we're just doing our normal thing. Now again, this is a fairly small Ka, so we can assume that relative to our 0.3, this x is going to be pretty small. Okay? We're going to make that assumption just like we did in the last chapter. So what you end up with here is 1.8 times 10 to the negative fifth is equal to x, instead of x squared here, it's going to be x times 0.30 divided by 0.30. Once we make our simplifying assumptions, that 0.30 minus x is basically 0.30, and 0.30 plus x is basically 0.30. Alright, now notice, these just cancel out, so our x here is just going to be equal to 1.8 times 10 to the negative fifth. Okay? And it's asking what's the pH of this solution. So the pH of the solution, the X we just solved for is the H plus concentration. Okay, so now if we just take the negative log of that number, then it's 4.74. And that's our pH, okay? Now, it would be interesting to just calculate, just very quickly here, if this was a normal x squared over 0.3, if we didn't have this initial 0.3 in here, just to see what the pH of the solution would be then. If you do that, 0.3 times the 1.8 times 10 to the negative fifth, take the square root of that, and then take the negative log of that number, our pH is actually 2.63, okay? So if we didn't have that acetate in there, that acetate ion in there to begin with, the more of the acetic acid would dissociate, would have more H+, and that would lower our pH. So this is a common ion thing. It actually causes the pH of the solution to go up a little bit. And again, another way to look at that is we're adding an acid and its conjugate base. So we would expect the pH to go up a little bit. Rather than just adding the acid into the solution, we're adding the acid and its conjugate base at the same time. Okay? All right, another practice problem. Calculate the pH of a solution containing 0.085 molar nitrous acid and 0.10 molar potassium nitrate. Okay, this one's not quite as nice because the numbers aren't exactly the same. So what we'd have to do, again, same basic idea here. We need to figure out the relevant equilibrium. And the relevant equilibrium is going to include HNO2 and the NO2 minus. All right, so if I write the equation for the dissociation of HNO2, that's going to give me both of those species in the reaction, okay? I'll just make my ice table. Concentration of the HNO2 is 0.085 molar. Again, we're going to assume 0 on our H plus at the beginning, but we've got some NO2 minus in that solution because of the potassium nitrite. We have 0.10 molar solution here, okay? So then again, minus x plus x plus x, 0.85 minus x, x, and 0.10 plus x. All right. Now the Ka for this one is actually up here. It's 4.5 times 10 to the negative fourth. Okay. So all we do is plug this into our expression. 4.5 times 10 to the negative fourth is equal to x. And again, we'll make our assumption here. X times 0.10. Those are the two products divided by 0.085. Okay. And once we work all this through and solve for x, then I'm getting an x of 3.8 times 10 to the negative fourth. Okay, and again, that's our H plus concentration. So if we take the negative log of that, that should give us our pH. And our pH should be about 3.42 on this one. Okay. So again, that's a higher pH than we would expect if we just had the nitrous acid in there by itself. Okay. All right, calculate the pH of the following: a solution made by combining 50 milliliters of 0.15 molar acetic acid and 50 milliliters of 0.20 molar sodium acetate. And the Ka of acetic acid is 1.8 times 10 to the negative fifth. Okay. The only thing that's different about this one is that we're going to have to refigure our concentrations here because they're giving us the concentration in the initial volume, but once we add these two together, then we have a volume of 100 milliliters of solution. Okay. So on this one, we'd have to do a couple M1 V1 equals M2 V2 calculations. Or you could just notice something fairly convenient here. We're doubling the volume. That's going to cut each of the concentrations in half. Okay, so our new concentration for the acetic acid, actually, let me just go ahead and write equilibrium here. So HC2H3O2, H plus C2H3O2 minus. Okay, and then when we make our ice table, the only thing you have to be careful of here is when you're plugging in your concentrations, they need to be half of what is given to you. Okay, so 0.15 divided by 2 would be 0.075. That's the acetic acid concentration. H plus, again, we're still going to assume is 0. And we've got 0.2 molar sodium acetate that's going to be 0.10 molar once we double the volume of the solution. Okay. If you want, if you're not, if that's not clear to you, then just plug these both into M1 V1 equals M2 V2. All right. So this is your V1. This is your M1. Your V2 is 100 milliliters once you add the two together. And then you should be able to solve for your M2 on the acetic acid. Then you do the same thing again for the sodium acetate. This would be your V1, this would be your M1, and then use the same V2 up here because it's going to be 100. Should give you the same numbers that I just plugged into the ice table, okay? And at that point, it's just exactly the same as the last two, so I'm not going to go over that again because I don't think we need to. You can work that out if you want to. Basically, it's just the minus x plus x thing, and then just plug that into your equilibrium expression. Okay. All right. Calculate the fluoride ion concentration and the pH of solution that is 0.20 molar in HF and 0.10 molar in HCl. Okay. So this one is not as immediately obvious. Okay. What the common ion is. But it's obviously not the F minus this time. Okay, so what these two have in common is they actually have some H plus in common. Alright? So again, same process, it's just a different common ion this time. So our relevant equilibrium is still going to be the weak acid equilibrium here. H plus F minus. Okay? When we put HCl into solution, the main thing that affects that solution is now we have some H plus, because this thing is going to completely dissociate, right, into H plus ions and Cl minus ions. Okay, so if I do my ice table on this one, now what I have is an initial concentration of HF, which is 0.20. I don't have any F minus initially in this solution, but I have an initial concentration of H plus already. Okay. And that H plus concentration is 0.1 molar. Because we just assume, that's a 1, we assume that the HCl completely dissociates, right? So, same process, you just have a different common ion this time. It's the H plus instead of the anion, which is what we've been doing, okay? So then, same thing, minus x plus x plus x. And this time we're trying to figure out the fluoride ion concentration. So we're going to be solving for x here. That x is going to give us the F minus. Let's see, we need the Ka for HF though, which is 6.8 times 10 to the negative fourth. Okay, so then we just plug that all in. 6.8 times 10 to the negative fourth is equal to x times, and again I'm making my simplifying assumption here, 0.10 divided by 0.20. Okay, and if I work all that out and solve for x, I end up with an x of 1.4 times 10 to the negative third, or 0.0014, however you prefer to write that. Okay, so there's your x. Now, every once in a while, it's probably a good idea to just practice checking the simplifying assumption to make sure that we're on the right track. All you have to do here is take your x, your 1.4 times 10 to the negative third, divide that by the initial concentration of the HF, which is 0.2. and then multiply it by 100, and that's 0.68%. Okay, so we are well within our rights here to make our simplifying assumption on this one. All right, so this x, that ends up being the F minus concentration, okay, because we just solved for this. So there's the answer to the first part of the question, okay. Now the second part is the pH of the solution, okay. Now, I want you to notice something here. When we add 0.1 plus 1.4 times 10 to the negative third, you get 0.101. To our number of sig figs, that's still just 0.1, okay? So again, that's the reason we made this assumption here that 0.1 plus x is basically 0.1. So the assumption that you can make here is that really the bulk of the H plus, the large majority of the H plus here is coming from the strong acid, not from the weak one, okay? And so because we have 0.10 molar strong acid, we can just use that concentration to figure out our pH of the solution. So we've got 0.10 molar H plus. So we take the negative log of 0.1, that gives us a pH of 1. Okay, and that's that. The ionization of a weak base will also decrease when a common ion is added, so this works for bases just like it does for acids. So here's an example problem for that. Calculate the pH and the trimethylammonium ion concentration of a solution. That is 0.075 molar in trimethylamine and 0.1 molar in trimethylammonium chloride. Okay, this one, it might be a little bit tougher to see initially. Did I mess that up? I may have messed that up. Hang on, let me check that. Because I think I put an H in there when it wasn't supposed to be one. Trying to find it here. Alright, let me pause it for a second, because I need to make sure that I didn't mess up that trimethylammonium chloride. I have a feeling that I did. I don't think that H is supposed to be in there. Give me just a second. Okay, I apologize. I looked it up to make sure, and that actually is right. So what I realized after I saw that was right is that I need that H there. Because what's going to happen here, this is harder to see, but this is actually a salt. And so what's going to happen is this is going to dissociate into CH3 NH with a positive charge and Cl minus, okay? So the Cl minus we don't care about, but this right here, this is going to be the conjugate acid for the base trimethylamine, okay? And so that actually is right, so I apologize for that. I wasn't thinking straight on that one. Okay, so what we have to do here is basically write our relevant equilibrium expression. So that's going to be CH3N plus H2O. Whenever you're writing a weak base equilibrium, you have to include the water. You can't take the shortcut. And so what's going to happen here is one of these hydrogens is going to attach itself to the nitrogen here. So we end up with CH3 NH plus OH minus, okay? So there's our equilibrium. And that one's a little bit tricky. Obviously, it kind of tricked me. So the weak base ones sometimes are a little bit more difficult to see, but you just got to remember what a base is doing is it's actually taking a hydrogen from the water, okay? So our initial concentration of trimethylamine is 0.075. Okay, we don't really care about the water here, so we can kind of X out that column. But we also put in 0.1 molar trimethylammonium chloride, and that associates in a 1-to-1 ratio, so that's also our concentration of the ion here, okay? And then we're going to assume we have none of the OH minus to begin with. So then we do everything just like normal. This is going to be a minus X going to be plus x and plus x. That gives an x down here. This is 0.10 plus x here. Okay. So then all we have to do is know the KB for this, which I did not write in the notes. Not doing well here. Give me a second. Rather than having you sit here on the video, I'm going to pause it, look up the KB for this, and I'm going to lose all my work when I do this. I'm actually going to keep it this time. There we go. Okay, sorry about that. So it's 6.4 times 10 to the negative fifth. KB here. Okay, so that gives us our KB. And so then you just plug in everything in like you normally do. So 6.4 times 10 to the negative fifth is equal to 0.10 times x over 0.075. Okay, so then once you do that, solve for x here. We made our simplifying assumption, by the way. I'm getting x to be equal to 4.8 times 10 to the negative fifth. Okay, so they're asking for the trimethylammonium ion concentration. Okay, well, that's kind of tricky because they basically gave you the trimethylammonium ion concentration. It's 0.1. Okay, because we made our simplifying assumption here. If we add this x to 0.1, it's still just going to be 0.1. Okay, so the answer to that is it's just 0.1. This concentration right here, just like it was to begin with, because we're not getting much extra there from the dissociation or the reaction of the trimethylamine with the water. Okay, but we can use that x. That gives us our OH minus concentration. And so we can use that to calculate our pH. If we take the negative log of that number, that gives us a pOH. That's where you have to be careful. It gives us a pOH of 4.32. So then we can subtract that from 14, and that's going to give us our pH, which is going to be 9.68. Okay. Now again, I would expect that the pH of trimethylamine in water would be higher than that, okay, because we put some of its conjugate acid in there. That's going to lower the pH of this solution just a little bit, okay? All right, so that's that. Sorry that last part took me a little while to work through. We'll see you guys in class.